Very good afternoon to everyone. We are here live at IMPA, directly to YouTube and the world. And my name is George Subelli, and I'm one of the organizers of this event, together with Max de Souza, and Bruno Lupir, Marco Vejaneda, Rodrigo Targino, and Yuri Saporito. And this is the second mini course of the day by Professor Tom Hurd. He's going to tell us about the Eisenberg-Noe paradigm for financial systemic risk. So, Tom, thank you very much for being back to Rio and being available to give this mini course, which is for us an honor and a pleasure. Yes.
Thank you, George. It's really great to be back. I was here almost 8 years ago. That was the last time I was here. But I was also at the Rio conference in 2007 in Buzios. So I'm going to work from over here. I'll probably use the blackboard from time to time. So, so the title reflects my enthusiasm for the Eisenberg-Noe model. I checked that paradigm exists as a word in Portuguese. Almost paradigma?
Yes. Correct.
Okay, good. So, so you know what I mean by that word. So I don't know if my computer is going to do that, turn itself off. I thought by plugging it in, it wouldn't do that. Okay, so so I just arrived. Got off the plane 2 hours ago, came over here, and so we'll see what comes. So you notice in the bottom right corner, you can see we're on page 1 of 130. I've got far more slides here than I intend to tell you about, but I couldn't decide on the plane which ones I wanted to give and which ones I didn't, so I just left them all in there. So. Some of you may know that I've published Springer briefs on the subject of systemic risk in financial networks. So much of what I'm going to talk about today is derived from the book. I'm treating this as a mini course for students, and so not as a tremendously innovative or state-of-the-art of systemic risk analysis, but more sort of foundational. So the book was a personal work, so so much of what I'm going to talk about is in chapter 2 of the book. So I always have to start with a definition, and I was here in 2011, and I gave a little mini course, and that was one of the first times I used Stephen Schwartz's definition of systemic risk. So that definition still seems okay. There's been massive amounts of, the field has expanded enormously since 2011. It's been taken up by academics, but also in a big way by researchers in central banks and regulatory agencies. So, so I'm sure other people have attempted to improve on this definition, but let's just say, you can read it for yourself, but the idea is that an economic shock triggers a major market or institutional failure that leads to a chain of failures in the markets and a chain of significant losses in financial institutions. That's the first part of it. But what was important was the second part as well, resulting in increases in the cost of capital or decreases in its availability. This is the liquidity aspect, and often evidenced by substantial price volatility. So the takeaway message is that we want to study cascades of shocks to banks and general financial institutions, and related to that, general drop in liquidity. And so the focus of this area is to understand contagion, not just correlation. So things can happen at the same time, but not have causal relationships. But we're very interested in the causal relationships, the transmission of shocks between different institutions. So maybe I won't talk too much about Andy Haldane's talk. It's pretty old, but it inspired me. I started working in the subject in 2009, and this is the first thought piece that I read about it, about the recent financial crisis of 2008, which you remember was brought to a boil on the weekend of the collapse of Lehman Brothers. It was also essentially the collapse of Merrill Lynch. It was also the collapse of AIG. So Andrew Haldane provocatively compared that event to a major epidemic that broke out in Toronto in 2002, the Sars Epidemic, and I don't suppose some of you remember that. It was a big event in Toronto. 40 people died in a matter of a month or two, frontline health workers. But it could have been much worse. I remember my colleague, an epidemiologist, he said he feared possible million of cases or more. So these kinds of contagious effects are thought to be manifestations of complex adaptive systems. So, oh, well, this is just a schematic, and you see what's driving the crisis, or what's the leading into the crisis, is a collapse of financial indices, which is sort of an overall degrading of the health of the financial system, to the point that it became susceptible to single events such as the collapse of Lehman Brothers. So things degenerated in the system till middle of 2000, till late 2008, and then, as you see, in September, all hell broke loose, and literally dozens of failures of banks around the world within the subsequent weeks. So this is just a list of the bank failures in September and October of that year, just to remind you of what was going on. And in November, the financial mathematics community in Toronto got together and said, we got to study the system. And so that's essentially, what's going wrong here. And so that's when I got interested in systemic risk. So, okay, so anyway, the summary of Haldane's thought piece was that networks arising in multiple areas in natural sciences and in engineering, they're complex and adaptive, and typically they're robust by design to everyday shocks. They're very resilient, but they have a certain fragility. If you hit them in the wrong way, they might just fall apart. And of course, these systems are too important to just let them fall apart. So you need to know how to intervene to restabilize them when they're falling apart. And there should be a lot to learn by studying other kinds of networks when you think about financial stability. Okay, well, my main takeaway from that was I wanted to study network science and to work out some basic modeling structure for systemic risk. And I was, as a mathematician, I cared about the kind of mathematics that was going to arise, but it also wanted to be adaptable, flexible, scalable, and eventually allow for all kinds of different types of financial institutions and different kinds of interactions and different channels of contagious shocks. So today I'm going to really go over some of the different manifestations of systemic risks, some of the channels that have been identified. And I'll try to put them all into the same language of this Eisenberg-Noe paradigm. Okay? So, but before getting into any kind of specific model, I just like to stimulate people to think about what is it about a system that's complex like the financial system, and what is, and specifically what could be driving instability in the financial system. Well, Hyman Minsky said it. He was a thought leader. I can't remember when this quote was. It's probably from the 70s. But he identified the fact very critically that during long periods of stable financial growth, financial practices evolve and take on more risk over time. So, and that risk makes financial instability more likely. So his quote is, stability, I like it because it's paradoxical. Stability, even of an expansion, is destabilizing in that more adventuresome financing of investment pays off to the leaders and the others follow. So, okay. So somehow financial systems naturally build up into a dangerous situation, and they build up during normal market periods, during periods of financial prosperity. Okay. So another idea that I like to talk about is self-organized criticality. So this was a very fashionable thing in the early 90s. So the physicists started thinking about chaotic systems in a big way. And if you just catalog some of the types of cascading that you see in natural systems, floods have this cascading nature, snow avalanches, forest fires, and then in an engineering context, cascades of load shedding and power grids. So these are all complex systems that exhibit the kind of cascading events that maybe we think are active in financial crises. So, okay, so a little bit more about self-organized criticality. So, I don't know, has anybody looked at the sand pile model? Has anybody thought about the sand pile model? Hands up that you know what the sand pile model is. George knows, because he heard me talk about it 8 years ago. Max, you remember? Yeah. Stefano? Yes. Okay, so basically what you do is you've got a round table, and okay, and you pour sand on it. You just start trickling sand into the middle of the table, and we all know what happens. The sand builds up. Okay? So the sand creates a little pile that gets bigger, and what happens? It fills the table. Okay? Of course. And so eventually this pile grows, and finally, you're in a situation where every additional grain of sand that you add has really no place that it's sure to rest. So, and what happens, of course, is a grain of sand that's dropped on the top of the pile can create a little seed of a cascade or a mini avalanche. And so every additional grain of sand is likely or may not create. So what the point is that every grain of sand that goes on the top, as sand is, there's no space for additional sand, so stuff has to fall off the table. So the question is, how big are for every grain, what's the distribution of the size of the cascade that it's likely to cause. So many grains do not directly cause any grains to fall off the table, but some grains may actually trigger an avalanche of 1,000 or 10,000 grains. So that's the idea of the sand pile model. And that was published in 1987, I guess. And in the paper called Self-Organized Criticality, Per Bach, who died not long after this, I think, was the key person responsible. So I really liked the book, Per Bach's book, How Nature Works. It's a great name, How Nature Works. So the Wikipedia definition is here. So the key idea is it's property of dynamical systems that naturally go into a critical point, and their macroscopic behavior displays a kind of scale invariance. And it's very reminiscent of phase transitions in statistical mechanics. But unlike typical phase transitions, you don't need to fine-tune any parameters to get to it. It's just the natural building up of sand that gets to the critical angle in the pile, and then when it hits the critical angle, you get these avalanches of all different sizes and scales. And this is supposed to explain fat tail statistics that are observed all the time in nature. Okay, so I kind of thought that sand piling might happen in financial markets. And interpreting Minsky's statement, a long period of stability may allow the system to build up into a critical state, and such a state might then be very susceptible, and you can have a large crisis that will follow and be triggered from a relatively small event. So that was what Haldane's message was. You're looking for large-scale disruptions that are triggered by actually relatively small events. Another important reason for me to say this is because the way you study self-organized criticality is you have to be in very large systems, and the models are essentially stochastic. Okay. Shall I? Yeah. Okay, so it's Saturday afternoon. I had a long flight. I sort of, well, let's keep it easy. So why is it that the financial markets tend to become destabilized through periods of financial stability? So Adrian and Shin in 2009 wrote this really beautiful paper called Liquidity and Leverage, and it goes as basic as looking at a household's balance sheet and asking about leverage. So here's this is a math institute, so I'm happy to talk about household finance. Okay, so when you take your $10,000 and you want to buy a house, you borrow $90,000, and then you have the financing for a $100,000 house, which is represented on the balance sheet, obviously like that, $100,000 in asset. You own the house, but you owe $90,000, and you have the equity, which is the remainder, which is 10. So this is a leverage ratio of assets to equity of 100 to 10 or 10 to 1. Okay, but the important thing about leverage, of course, is that you can either make a lot of money or lose a lot of money when the underlying asset changes its value. So if the asset moves up to 101, your debt is still 90, and you have the difference, which is now 11. So a 1% move in the assets translates into basically 10% movement in your equity. Okay, so there's the graph, how your leverage changes when the asset changes prices. So your leverage ratio, when you have $11 of equity and $101 asset, is that 0.9 or 9 to 1. Okay. And so they show a graph that shows that household leverage does respond according to that curve. Quarterly changes in the asset value correspond to quarterly changes in household leverage, and it's the same shape for households. But if you do the same thing for commercial banks, it doesn't look like that at all. It's actually fairly concentrated that the leverage growth doesn't change. So when the asset price, in a time of rising asset prices, they maintain the same leverage ratio. And then American investment banks are extremely aggressive, and rather than just maintaining a constant leverage, this shows that they over-lever as the economic conditions improve. Right? Okay, so what happens when you implement a constant leverage strategy like a commercial bank? Well, when the asset value rises to 101, your leverage has gone lower than 10, and so you lever up by raising $9 more debt, and then you buy 9 units of the asset, or $9 of the asset, and now you hold 110, and of course your equity was still 11, and that puts you back to your leverage target of 10. So a 1% rise in security values translated into a 10% increase in the number of assets you held. So you really, the higher the price, the more you buy. So, that creates the leverage spiral. So if you have a bunch of leverage targeting institutions, then as the prices go up, their balance sheets improve. They adjust their leverage by buying more assets, and of course that's the upward leverage spiral. Okay, the opposite is also going to happen. So when the assets decline in value, then that triggers an aggressive selling of the asset and leading to a downward spiral, which could be quite dramatic in a crisis situation. So sure enough, all the investment banks that led into the crisis were aggressively over-levering, increasing their leverage ratio during the period up to 2007. At the same time, they became a bigger percentage, of course, of the entire financial market. So the red curve showing market share of the investment banks rising. Okay, so anyway, that's kind of my introduction. I thought I would just say a few generalities like that. Is there any questions? So, okay, so now we want to build some models. And so So it's become standard to start with the Eisenberg-Noe model and to consider what are called default cascades. So the original paper wasn't really about systemic risk. It was an abstract, it described an abstract payment system. And the agents in this, or entities in the system build up a network of payment obligations. And then they imagine that at a moment in time, the system needs to be resolved or cleared. But they imagine doing this at a general moment in time when some of the entities are no longer fully able to pay their committed payments in full. So what's the fair allocation of all of these inter-entity payment obligations? So this was a very abstract, it was an ideal clearing system, and it simply asks the question, is there a collection of payment that solves a consistent set of equations that tells all the agents exactly how much they have to pay back and how much they will receive? Okay. So let's put up the balance sheet that's going to be the workhorse for much of today. So it's pretty simple. So their agents have, well, actually interpreting it a little bit, they actually didn't have Y and D, but our banks, our agents are now going to be thought of as banks, and on the asset side, the banks are assumed to be lending to the outside world. And borrowing from the outside world. Meanwhile, they're doing bilateral lending amongst themselves. So, so this is interbank liabilities and interbank assets. Okay, so just for completeness, so that we have the letters, so we can remember what the letters are when they appear, I'll try to stick to these letters. Actually, I'm going to be adding to the picture in a little while. This is good for a start. Okay, so so we have some obvious identities. So the balance sheet is supposed to balance. So the equity, there's two interpretations of equity, and I'm interpreting equity as a balancing variable. It's defined so that the balance sheet balances. So the other components of the balance sheet are valued as assets and liabilities, and equity is defined as the assets minus the other liabilities. Okay? So I'm going to be labeling the different banks by letters like V and W. And okay, so the interbank debt, of course, is a set of bilateral contracts with a borrower and a lender. So I'll use the letter capital omega for the exposure. And remember that the subscript V represents the debtor bank and the W represents the creditor bank. So this V owes W. So actually, omega is called the liability matrix. There's a bit of a confusion in the literature because often people write down what's called the exposure matrix, and then it's actually the transpose. So the exposure matrix, and then it becomes confusing even more because then they may or may not put the arrow in the same direction as my arrow. Okay, so you have to be careful. Okay, so of course the interbank assets is a sum over the column, the row index. Sorry, the column sum over the row index of omega, and the interbank liabilities is a sum over the column index. Okay, and finally, it's convenient sometimes, not all the time, to look at the debt ratios. Think of what fraction this exposure is across all of the interbank debt held by that bank V. Okay, so notice this is making the row sums equal to 1. Okay. So to make it memorable, I put it all up here in a matrix. So this matrix, the first n columns show all the assets of n banks, and the first n rows show all the liabilities and equity of the same n banks. And notice each exposure is pi times x. Okay. Okay, so the model works. It's extremely simple. A bank with negative, a bank whose equity is negative or 0 is deemed to be defaulted or insolvent, okay? And the converse, a solvent bank has positive equity. So apart from the marginal case, E equals 0, insolvent banks have insufficient assets to pay all their liabilities. Okay, so further, Eisenberg-Noe assume, actually, this is an extension of Eisenberg-Noe. I'll come back to this in a minute. The external debt, in the event that the bank is insolvent, the external debt is paid, no, to say it the other way, the interbank liability is strictly junior in seniority to the external debt D, and no interbank liability is paid until all of the debt D is paid. Okay. Okay. And furthermore, in part 1 of the assumption, all interbank debt has the same seniority. So that means all of these exposures, when V defaults, the exposures are paid in proportion to the creditors of V in proportion to the matrix pi. Okay? The second important assumption is there's no bankruptcy charges accounted for in this system. And the third thing is that external assets always exceed deposits in the original Eisenberg-Noe model. Okay, so just for completeness, Eisenberg-Noe had the parameter E, which was called the endowment, and that's the same as Y minus D. And that was assumed to be positive. Okay. So one of the things you have to get used to is the idea of taking vectors and taking component-wise operations, component-wise inequalities, and component-wise maximum and minimum. So just notice that I won't be writing vector signs over vectors. I guess it would be nice. Is there a pointer of some sort? Anyway, don't rush. But if one appears, I'll yeah. Anyway, we're going to be doing a lot of these orderings. So. Okay. Mm-hmm. Okay, can you actually see the red dot? Yeah. Okay, so all of this stuff should be obvious, but x is a vector. Okay, come on, we're having a fight here. Is that the Red Baron coming in and attacking? Is that you, Renee?
No, that's George.
George, okay. Okay, enough fun, come on. No pranks. Okay. Okay, so we're going to be dealing with n-dimensional vectors, and they represent balance sheet entries of the n different banks. And basically, balance sheet entries should be positive, so that means every component should be, or balance sheet entries should typically be non-negative. So you want that a lot of these vectors should be bigger than or equal to 0. Okay, so a hyperinterval is describable by two vectors. It's if you have an x and a y, where x is component-wise less than or equal to y, then the hyperinterval from x to y is the set of z's that are component-wise between the components of x and y. Now, I'm not this kind of, I don't even know what this theory of, this is actually kind of coming out of logic, and these things are examples of complete lattices, and it's not a subject that I've studied in my life, but so the structure of hyperintervals it has a structure of a complete lattice, which means it's a partially ordered set with a closed, every subset has a sup and an inf. Okay. So the Eisenberg-Noe problem is find the amount P for each bank that bank B has available to pay their debt. And then the total amount that each bank will pay will be split amongst their creditor banks in proportion to the pi matrix. So which means that bank W will receive pi. Now, that's summing over the row index of pi multiplied by p. So that's like p or this is like the transpose of pi multiplying p. Okay. And then this statement is that the clearing conditions that we desire are that for each bank, their p value will be the lesser of the total amount they're obliged to pay, which is x, or the total amount that they can raise in asset value after they've paid their debt, d. So in other words, PV will be the minimum of those two things. Y is the total external assets. This is the total amount bank V raises from their interbank debt. So that's, and then minus the amount they pay on their external debt. And so as a vector equation, that's the minimum of the x vector and the total assets realized minus the debt. And so that is a consistency equation. Solutions of the fixed point problem are called clearing vectors. So their main theorem is that this system has a greatest and least clearing vector. And the second one is not so important. And it turns out that under all clearing vectors, the equity of each node is the same. And basically, the equity of a node is going to be 0 if the bank fails to pay their complete obligation, and will be positive if they pay in full. Okay, so the proof is just the proof of 1 is simply that we have a very non-topological, this is very abstract theorem. It's much more general than, say, the Brouwer fixed point theorem. And it just says that the fixed point set of a monotone mapping on a complete lattice is itself a complete lattice, and the consequence is, since complete lattices are non-empty, they have a maximum and minimum element. So okay, so just need to. It's trivial to see that the mapping in question is monotone. It's trivial to see that it maps the hyperinterval with 0 on the lower left and x on the upper right. That's a hyperinterval. And this mapping maps the hyperinterval onto itself. And the hyperinterval is a complete lattice. So that's the proof. Okay? Right. And let me not give the second part. So, so if you want an exercise, if you're a student, that there was an exam, then I'd put this on the exam. So solve, there's an algorithmic way to find these fixed points. And when it's labeled like that, if y minus d has positive numbers in it, then there's one solution. If you're looking for a counterexample where there's more than one solution, then there's very few of them in this model. Basically, the only counterexamples to uniqueness of this fixed point are when y minus d is exactly 0 for all banks. And so, okay, well, that's just the basic Eisenberg-Noe model. And let me now talk a bit about how you're going to want to extend it. Well, one thing is you don't want to necessarily have all the debt that's external to be senior to the bank debt. And so you can add a component, you can add a node 0 to the network, and that will represent the external system that's lent to the banking system at the same seniority of interbank debt. So that just allows you to interpret the same formulas in a more general financial situation. So for free, we can think of one more bank that represents lending to the system by the exterior and with the same seniority of the interbank debt. So that's good. Now, I actually am pretty interested in y less than d. So the third assumption in the Eisenberg-Noe model was y minus d bigger than or equal to 0. And it turns out, because we want to treat this as a paradigm for modeling lots of different things, we don't want an artificial restriction like that one. So what can you say when y is less than d? Another important thing is that the Eisenberg-Noe picture is looking for this clearing vector, but it doesn't really ask the question, how does the market achieve the clearing vector? How does it find the clearing vector? And of course, to solve fixed point equations, usually you solve by iteration. So I'll just say now that we're going to get the Cascade picture because we're going to solve the Eisenberg-Noe model not just as finding the abstract characterization of the fixed point. We're actually going to achieve the fixed point by iterating the fixed point mapping function. Okay? So that's the interpretation that that fits with our idea of contagious defaults or contagion shocks going from bank to bank. Okay, a fourth thing that's really important is the Eisenberg-Noe model is a terrible model for systemic risk because there's no bankruptcy costs. So if you think about it, there's no possibility of amplifying the contagion. So I'm very interested in amplified versions of the Eisenberg-Noe model. And you can get that by modeling costs that are incurred when banks are insolvent. Okay. So what about the cases with the general case when y may be less than d? Well, we'll just focus on the very last equation. It turns out that that it just adds one more condition on the fixed point equation. Namely, you need to make sure that p doesn't go negative. So you take 0 in place of a negative value for p. So that is the more general, what I would call a standard form of Eisenberg-Noe model. And it comes with this lower bound through the extra max. Okay, and notice that it's autonomous, that the p variable arises. The q variable is when you want to know how much external debt may not be paid, or actually the amount of external debt that will be paid. That's q. So when y is less than d, then some of the external debt will not be paid, quite likely. Okay. Now, I was thinking on the plane quite a lot about the uniqueness of the fixed point. So fixed point exists for the general case, but the uniqueness statement is far more tricky. And in fact, it's trickier than I wrote in my book. So I apologize for having an unproven assertion in my book. I think it's true, but it's embarrassing. I shouldn't be saying it, but it's not proven in my book. Okay, so see if you can find if you like, the incorrect proof. But it's, in my mind, it's still, it is tricky to figure out when the fixed point may be not unique. Okay. Now I really want to start going to this point of solving the Eisenberg-Noe model through iteration rather than just abstractly characterizing it. Because now I want to start talking about using the language of contagion and shocks. And so exactly equivalent to the Eisenberg-Noe model, pretty much, is we start with balance sheets at time 0. Just at the moment a sufficiently large trigger has happened. Okay? So the trigger has to be big enough that at least one of the banks becomes insolvent. Okay? So I'm going to introduce an idea of a buffer variable. And buffer variables are things in the balance sheet, but they're allowed to go negative. So this delta is the default buffer, and it's like equity, except that it's going to go negative. So
like some kind of insurance, bank insurance?
not
FDIC or something like that?
I'm not thinking of it like that. So you're right to raise the question of deposit insurance. My view on deposit insurance would be that we'd like to compute the Eisenberg-Noe fixed point in order to determine what the government is on, the FDIC is on the hook for to recover the lost amount on insured deposits. So that would be a consequence of this. So I'm not modeling the actual insurance. So now delta is the balancing variable that makes the balance sheet balance, but when you put mark-to-market valuations, this can go negative. Okay, so now we solve the fixed point condition by iterating, and we'll count the number of iterates by n, and we'll just think of it as daily updates of the balance sheets. So after n cascade steps, the amount that bank V thinks it should pay is called PNV. And of course, at time 0, P0V is the fully committed value X. Okay, so I now want to introduce a threshold function. Let me do the calculation here. So the nth step of the Eisenberg-Noe cascade is here at the bottom of the slide. Let me just do this because it's not 100% transparent what's going on here, but I want to do it for you. So this is our Eisenberg-Noe function. Okay, and of course Pn is defined to be f of Pn minus 1. Okay? So I want to write that using this threshold function h. So let's just work it out here. And notice what's inside the threshold function. It's got this buffer variable. Okay? So let's work out what f is. And what I'm going to do is I'm going to write y minus d is delta plus x minus z. Okay, so that goes in here. So Pn is equal to the max, 0, min, then I've got x, and I've got delta. Now this is delta n minus 1 plus x, And now z is minus z is minus p star times x. Oh no, that's p. Sorry, this is the initial. This is the interbank asset at the time, at the beginning of the crisis. So it's the full. It's assuming everybody's paying their full amount x, and then plus pi star p, comma, and that's that. Okay. Now I want to factor out x. And that's what we get. We get delta n minus 1. And then we get minus pi transpose star 1 minus p n minus 1 over x divided by x. Is that correct? No, sorry. No, I want to change this to omega. Right. Yeah. So that actually, so inside here, this is what I call the h function. So this is h evaluated. Oh, I forgot, there's a plus 1 here because there's an x here. Right. So this is the h function evaluated at delta n divided by x. Okay, so you see what's going on here. This thing in the numerator is the previous buffer minus a positive term, which is a shock. And so p over x is less than or equal to 1, so this is a positive number. Omega has got positive values in it, so there's a minus. So the buffer at step n minus 1 is diminished by this shock, and that's the formula for the new buffer. So the new buffer is delta n minus 1 minus, and I'll write it out, sum over the counterparties the full exposure multiplied by 1 minus, and now Pn minus 1 is given by the h function. So it's h delta n minus 1 divided by x. So you see the Eisenberg-Noe cascade can be thought of as the buffer is getting impacted sequentially as the amounts available to pay by the counterparty banks drops during the crisis. Okay? So each subsequent step, we tend to get an additional small shock. Okay? So this equation here shows that the default buffers alone can determine the state of health of all the banks. And you see that the P vector is the total commitment multiplied by this h function. The h function is this threshold function, and it looks like this. Minus 1, 1. So that's h of x. So what h represents, it's the fractional recovery of the interbank debt when x is equal to delta divided by x, so the variable x. So you look at the ratio of delta to the total interbank debt, and when that's negative, then the recovery is less than 100%. Okay, so that's the picture of a default cascade mapping, and so this is where represents the contagion that we talk about in systemic crises. Okay, so rather than just say there exists a fixed point, we realize the fixed point by stepping through an actual crisis spread out over time. Of course, the time scale depends on the actual type of shock that you're talking about. So,
how fast is the convergence?
It's subtle how fast that converges, but basically, what it really comes down to is the fact that, I guess, that 1 minus pi, the identity matrix minus the pi, one way to look at it, actually with a transpose. So built into this convergence is the sort of resolvent expansion for the identity minus pi. Now, pi is a matrix with row sums equal to 1, right? Well. However, usually you apply it in a projected onto a subspace where the row sums are not equal to 1, and that gives you convergence. So it's subtle. Okay, so I should say dot, dot, dot. Okay, so it can go very fast if there's not a lot of cascading happening. Then most of the variables are paying in full, and then you're only computing pi restricted to the defaulted banks. And on that subspace, the row sum might be much less than 1. Okay, so I guess this is just too many words. So notice point 5. We're iterating starting at the maximal x. So by the monotonicity of the cascade mapping, we're going to achieve a fixed point in the limit from the top down, which goes to the maximal fixed point in case the fixed point is not unique. Okay? So that we'd call G plus. Now, what is the data that it depends upon? G plus depends explicitly on the initial delta 0 and the initial exposure. So the fixed point, the maximal fixed point, is a function of those. So basically, the stability of the system is determined entirely by the buffer and the exposure matrix or the liability matrix. So none of the other balance sheet components actually affect the crisis. Okay, so that's good. It's actually quite a lot simpler than I made it out to be in the first place. Another point is if you start by assuming every bank pays 0 rather than x, then you get a monotone increasing sequence that'll converge to the minimal fixed point. Okay. Right. Now the h function over here, remember that the value between 0 and 1 is the fractional repayment. So you can see off at a glance when you pay in full and when you pay partially and when you pay nothing. Okay? So, okay. So let me now talk about bankruptcy costs for a minute or two. Yeah. What time is it?
We're talking for 1 hour and 10 minutes.
Okay.
Would you like to have a break?
Sure.
Since
Yep, I'm at a break point, so yeah, good. Okay.
Thank you so
Okay. Thank you. Thank you for your patience.